Hey everyone, welcome back to Unum Space. As part of the system design playlist, today we are going to talk about a system design problem which was asked in a recent OpenAI interview. The problem is to design a VS Code like IDE in browser. So let's get into it. Before we actually design this, let's try to understand how it actually works in the real world. I'll be sharing an example which I have opened in a couple of websites. So the first one is the replit.com. It is also an online IDE. It's a sharing code space which also has agentic features, but we're not designing that for the simplicity. So this is a Rust project which I have opened from my GitHub. So as you can see, there is a file tree where you can see all the folders, and on the left side you can see all the file content. Here if you can see that all the folders are not opened by default. If you click on a folder, it will take like couple of seconds before it loads the contents of that folder. Just try to understand that. And yeah, now if I open Brew, it takes like a slight latency and then it opens the folder. So the reason why I am specifically saying that is all the data or all the files are not loaded in your browser at the time of this website loading. All this data is lazily loaded in the website. That is very essential to actually design a platform like this in browser. And you can also invite people to join your code space. So this is a single code space, and you can invite people and they can edit parallelly like you at the same time. This is also very essential before you design a system like this, because in a system where you want everything to be online, you also want that system to be reused or shared across people so that they can do their changes in the same workspace. There are some issues, there are some caveats which you will face when you are designing this. We will be discussing about that in this system design. So coming back to our design, before you design, there are some concepts which you want to understand, like conflict resolution, which I have talked about in the collaboration, wherein if you have a single file, there are multiple people who are making the changes in the same file, just like Google Docs. If you look at Google Docs, it can be shared across multiple people, or Google Sheets, like an Excel file which can be shared across multiple people. What if multiple people are making the changes on the single line, and how does the server handles that? Does it keep the data of one user and just throws away the other user, or it does something else to actually preserve the changes of both the users? So this concept is called conflict resolution. There are multiple algorithms which can be used for this, but famously there are two algorithms. One is the operational transform and the other one is the CRDT, which is conflict free replicated data type. So we'll be primarily talking about CRDT here because that's more easier to implement, and that is also easier to remember, so that you can talk about that in the interview. So just to give an introduction on the operational transform, how it works is that there is a central server and all the users are connected to that server. If more than one person is making changes in the single file, all the changes are gone to that particular central server, and central server kinds of takes care of the collaboration and conflict resolution. So this is used by Google Docs. This is not very scalable, and we have another thing called CRDT, which is conflict free replicated data type. So this is not a system, but rather than it is a data type which can be used to resolve conflicts without losing any data of multiple people. So how it works is that every character in a document gets its own unique ID. I'll try to give you an example, running example after that. So here every character will get a unique ID, and if we are adding a character in between two characters, that will also get a unique ID. So if a person is adding one character at the end and another person is adding one character at the beginning of the same word, both of these new letters gets their own unique ID. The server kinds of combines both of these changes and resolve the conflicts. So this is primarily used by Figma, Apple Notes, Y.js and AutoMerge. These are the famous shared spaces where multiple people involved in making some changes. So this is an interactive example. So in the beginning we have HELLO, and these are the two users, Alice and Bob. They can see the same text in the beginning, and if you see the ID 0.100 is attached to H, so that's the unique identifier given to that particular letter, and 0.200 is also assigned to E. Like the IDs are same because essentially this is the same document shared across the users. So let's say we are adding a character in the beginning, the Alice is adding a character in the beginning and X. So now this character got 0.050 as the identifier. How did it decide that unique identifier, right? So this is a floating point, and in an infinite number line you can have a mid number between any two characters. So let's say I'm adding one character here, I will get 0.150 and 0.2. So 0.200 is intact. If you can see, E unique identifier is intact. I'm just creating a new unique identifier for the new character which is being added. So this is the event log. Alice inserted X between these characters, between H and the first, and this new character between H and E. So let's say Bob is adding at the end, right? So now here they are making changes for the exact word. The changes are not yet stored in the database. These are local changes to their code spaces. And when does it sync? When they actually click on, maybe let's say Control S, or they have some configuration set up like save, auto save on for every 30 seconds. That's when it actually synced with the server, and server gets changes for multiple people at the same time. It will be synced. So let's say here I am syncing. So what it does is that as these unique identifiers are independent and there is no conflict here, even though they are making changes for the same word. So here, like at the end, these changes are synced, and both of the users will get the exact data. Here you have XEH, here you have XH and a new character, and the same changes are synced with the Bob, which is another user, and he also made a change at the end of the word. So that is also synced. So this is how CRDT actually work. You don't need to understand this entirely. You just need that there are some paradigms which will be used in the collaboration workspaces where there is a chance of multiple people doing the changes in the same file. If you want to learn more about this CRDT, I will add a YouTube link in the comment section. You can go ahead and learn about it. So the next one is the WebSockets. For the people who don't know, it is an API paradigm, application programming interface, where the server and the client have end-to-end connectivity, like two-way connectivity, where client can send data to the server and server can also send the data to the client. So in traditional HTTP APIs like REST APIs, only the client can send the data to the users, and the client can also get the data from the users. So it is prompted from client perspective. But in WebSockets, if a connection is established, and server can actually send the data without the client asking for it. So here we will be using this WebSocket primarily for virtual shared code spaces where there are multiple people who joined a code space and they are looking at a file where there is another person who is making the change. When the person make the changes should be synced with the server, and the other person who is also looking at this file should also get the data. So now that you understand CRDT and WebSockets, let's try to get down the functional requirements for this problem. Again, understand that you have a limited time, like 45 minutes for your system design interview, if you remove 15 minutes for the beginning and the end for questions and introduction. As this system design question has been asked in OpenAI, there are multiple things you actually have to cover because the OpenAI bar is higher and they pay really well. So for that reason, I have added a little bit more functional requirements than I have added in the previous YouTube system design. so that you can pick and choose not to add some functional requirements in your actual system design interview. But if I would have been in that situation, I would have been covering all these functional requirements. So first one is the user's login and the code base is protected by RBAC. RBAC means role based access control, where a particular project is actually protected, and even if there are multiple people who have the access to the same project, different people might have different accesses. So a person can have an admin access which he can view, edit, delete the project. He can do anything because he is an admin. So there may be some people who have view access. They can only view the data, they cannot edit the data. And there are people who have editor access, where they can view the files and they can also make edits for the files. So we want these to be implemented in a shared code space so that you can share the project for multiple people with multiple accesses. So the next one is the navigate the file tree of a workspace. As I've discussed in the actual system design, you should be able to navigate to each file in a project. So that should be a must for the system design we are developing here. So the next one is the view and edit file contents in the editor. Obviously we want to view the file and we also want to edit the file contents of our project in the editor. And search for files and across file contents. Here you would have two different searches. One, you want to search for, let's say, build, the file itself, and the other one you should be able to search for the entire file content, let's say project. So maybe that is part of in a file, right? You want to search in a file itself. And this is support all major languages with syntax highlighting. This is not essential and you don't need to mention in the interview. I think I didn't cover it in the current system design because we don't need that to be implemented. There are multiple libraries available which are called LSPs, language server, for each independent languages. So the next one is the terminal access to run commands in the workspace. Even if you are providing a workspace, you should be able to give them a terminal which should not be shared across the projects, because that is a catastrophic issue, where with terminal you will be able to have access for the actual file system. So we should limit that to a particular project or a workspace. And the next one is the real-time collaboration. This is a must, I would say, in a system design like this for a company like OpenAI, because there are many things to talk about this in an actual system design. So I would advise you to add this for sure, and feel free to remove some features above. So now that you have functional requirements, let's get into the non-functional requirements. I've added a little bit more non-functional requirements than the previous YouTube system design I've talked about. Like I said, this is an OpenAI system design, so you should be performing better than the average candidate. So the first one is the support large code bases up to 100 gigs per workspace. As there are many projects which have huge data, and we should be able to view the files in the browser, and as you know, browser is just an application in a entire system, and you don't want to load the entire 100 GB in your browser. You should be handling the lazy loading. Like if a person is actually viewing at your project for the root project, you don't need to load the subfolders for this folder, and you don't need to load the subfolders for this folder until they click on this. So it essentially, when they are looking at your project for the first time, you're just loading a list and there is no content. As in when they click on this, that's when you call the subfolders and get the data when they actually click on a file and load the data lazily. So this will help you to load the data lazily, and all the data is not loaded in your browser as and when they open a project. So the next one is edits are durable and stored indefinitely. This is very essential where there is a person who is making changes in the code and all of a sudden the server is crashed and the data is lost where they have done changes. So when they actually click on save, the data should be persisted indefinitely, at least till the user needs. So the next one is the real-time collaboration is consistent across all participants. So this is a classic problem of consistency, availability and partition tolerance. So here we should be having high consistency for the collaboration and high partition tolerance for multiple gigs of files, because here the projects are huge, can be huge. We want to store the data in multiple partitions if we actually wanted to. So what this means is that when multiple people are making the changes should be consistent and their changes should not be overridden by the other person. So like I said, if we use CRDT, then those changes are actually merged. If something goes wrong, then the users will take care of resolving those issues. The next one is the back of the envelope calculations. So this is just to get an idea on how much is the scale of the system, so that you can design the database, you can design which blob storage you wanted to store and stuff. So I just assumed that there are 10 million total projects, 10% of active daily, meaning 1 million active projects per day. They are opening, they are making changes, and there are 5 file edits project per day. If a user has opened a project, on an average we are assuming that he will be doing at least 5 file edits for a project. If we multiply with the 1 million active projects, then it is 5 million file edits per day. Then there is operational log. So operational log is that if you are making some change in a file, you should be able to store that operation as a separate entity, because if something goes wrong, you can actually replay all the operations and get the end result of a particular file. So here we have 5 million file edits and let's say 100 operations per edit, and you have 100 bytes for each operation, so which comes around 50 GB per day. That's not much, but yeah, we should be able to store this. And file version, this is used where you want to have backup of a particular file. So when someone saves a file, you can store a backup of that particular version, so that if something goes wrong, you can actually go back to that previous version of a file. Then there is collaboration sessions. As we have 1 million active projects per day, and each collaboration session, let's just assume, takes 200 bytes, so which comes around 200 megabytes per day, which is not much, but it is worth noting in a project. Then we have blob storage, which is the S3. Here we are using S3, but if your interviewer doesn't want to use S3, feel free to use maybe blob storage from Google. Here we have new projects per day, 1% of 10 million. So we have 10 million active daily projects. 1% of them are the new projects, which is around 100k projects per day. Average repo size, let's just consider 100 MB, and it depends, it is an average. There can be projects like 10 GB or 100 GB. On an average, the projects are 100 MB. And if you multiply with 100k, which we would get around 10 TB per day S3 storage. Then we have file edits stored as diffs. I design the system such that I'll store the diffs instead of the entire file. Let's say you have a big file and someone is making changes in a single line. You don't want to store the entire data of the new version of that file, right? So as I've discussed in the previous slide, I'll store the file version. When I say the file version, I'll not store the entire file contents. I'll store the difference of the previous file version and the next file version. If the user wants a particular version of the file, I'll just calculate the point in time backup of that version using all those diffs. We have 5 million edits, each edit 10 KB. We would get around 50 GB per day for just for the file edits. So now that you have back of the envelope calculations, let's go into the entities and the data model. So this is a tricky part because we have so many entities in the project. I'll try to lay down each entity and why I was thinking a particular entity to be an entity. So the first one is the user. We need a user as an entity, and here we have ID, email, username and auth provider. The auth provider is specific that some people register with Gmail, some people directly register in your portal in multiple auth providers. Then there is file itself. We will have a file by an entity, but here we will not store the data in this entity. We will just store the blob URL for that file. So each file belongs to a particular workspace, and each file will also have a file path. We are actually storing the entire file path for each file, just like an S3. In S3 you don't have folders itself, you have files with the entire file path, and it kind of calculates the folders based on the entire file path. And we also have size. So this is an optional, you can either have size here or you can calculate size from the blob itself. And timestamps, this timestamps is like last edited or last created, last updated, those kind of timestamps in the file entity. So then role as an entity, as we have discussed in the functional requirements, we will be implementing role based access control. We need the role as an entity so that you can attach this role for each user for each workspace, so to determine what accesses they actually have for that project. Then we have file version. Like I discussed, I will be storing file versions, and here we have ID, file ID, version number, the current version or all the versions, and blob URL. So here the blob URL will be pointing to a file version which will have the diffs of the previous file version. So it is not the entire file, it is just the diffs of file version. And it also has created by who created that particular file version, who made the changes exactly. And then there we have workspace. So what is a workspace? So workspace can be a project or a group of projects. That's up to you and your interview how to define that paradigm. But here I am assuming workspace is a single project. Each workspace will have a single project. And you have a workspace member. So when a person joins a particular workspace, that will be created as a workspace member, which will be having the user ID and the workspace ID and role ID, which role that particular user has for that workspace and when did they join, right? So if you want to find the role for a particular member in a workspace, you can just look at this table and find out whether they have access to this workspace or not. Then we have collaboration. So in collaboration we have workspace ID and user ID. So why do we have collaboration as a separate entity? So if a person is part of a workspace and they are actively making changes in a project, in the same project which is being shared by different people, so that is a collaboration activity, right? So there are multiple people in a single project. So we want to be able to find out people who are actually active in that particular collaboration for different reasons. You can show them in the UI that there are multiple people who are making the changes, or you want to find a particular collaboration user. If their connection is lost, you will establish a new connection for any reasons, right? You can store that as an entity, and you can also have a boolean like active, whether it is an active collaboration or it has been concluded or it is closed. Then we have operation log. So operation log is specific where they are making changes, deleting files, deleting content, adding content. Each operation is an operation log by itself. So we have a file version. When they actually save the file, that will create a file version. Here we have operation log for each operation, each keystroke they do. So now that we have all the entities, and this is the entity relationship model, we have user which can be part of multiple workspaces. That's why they have multiple workspace member. and each role can have one-to-many relationship between workspace member, because a particular user can have multiple roles as well. And for between workspace member and workspace, it is many to one relation. For each workspace there can be multiple workspace members, and between workspace to the file we have multiple files as part of the workspace, and for each file there can be multiple operation logs like we have discussed, and again for each file we can have multiple file versions as well. And in the collaboration, a user can be part of multiple collaborations, and a workspace can have multiple collaborations as well. So you don't need to draw this beautiful diagram in your system design interview. You just let them know that how these entities are related with each other. Now you have entities and entity relationship diagram. Now we want to design APIs. So this is a pretty huge list. Like I discussed, I am covering multiple features because it was asked for OpenAI, and feel free to remove some APIs if you actually don't want to implement. I always say that try to match your API design with your functional requirements. In the functional requirement, we first talked about the authentication and role based access for that particular user. So as part of that, we have auth and identity APIs. We have auth login, which starts either OAuth flow or the Google or traditional login flow. And when they log in, then it will try to call back with the access token, which is the JWT token, which the UI can store in the cookies and use it for multiple operations. Then the refresh, which refreshes the user's session, and then the logout, which logouts the user. So the next one is the workspace and members. This is very essential because there are multiple operations which can be done in a particular workspace. So first thing is that list workspaces. So for all these APIs, the authentication and authorization done based on the JWT token which was done in the previous slide. They logged in and their session token is stored in the session cookie. That cookie will be shared with all the APIs, and all the APIs will get the user's data from that session token. So first API is to get all the workspaces for that particular user when they open the home page. And the next one is the post workspace. This is to create a workspace if they want to create a new project or the workspace. And the next one is the workspace by ID. So let's say they click on a workspace, they want to look at the workspace for workspace details for that single workspace entity. And the next one is to invite, like workspace and ID and members. So this is a post endpoint. Here we are inviting a particular user to a particular workspace. So here we would use this post endpoint. So the next one is the get. Here you want to view all the users or the members part of the single workspace. You would use a get endpoint for that. And the next one is the change role. Let's say user has a particular role, they want to change their role. Now before they had read role, now they want to have write role. They can use this API to change their role. So the next one is the delete role. Now they want to, let's say admin wants to remove a particular member, or they want to leave a particular workspace, they can use this API. So the next one is the files, tree and search. So this is specific to the files. So here each file is part of a particular workspace. That's why all the file paths are part of the workspace APIs. So we have workspace, ID and files, and here you would send a particular path because you want to have files and folders for a particular file, right? So this is the API which you would call. And the next one is the fetch the file contents based on the file ID. So now that they have a file opened here, when they click on it, the data must be opened here. So that's where this API is called. And the next one is to create a file. So let's say I want to create a file here and add folder, some folder. So that's where this API will be used, post API, to create a file for in that workspace. And the next one is to edit a file, like either defs or renaming a particular file. All those are done as part of this workspace. So here you are making some change. You're not sending the entire file content to the backend. You're only sending the difference between the existing version and the new version. So that's why it has defs. Version is specific to the current version. So the backend decides the newer version which it creates. So the next one is to delete a particular file, and this is for search. So there are two search endpoints. One is to search full content, like you have workspace ID search, you're sending the entire query. And the next one is to search a file. So that's why you have workspace ID files / search. This will search the files based on the query which you will pass. And the last one is the collaboration and terminal. So I made sure these are simple to understand. So for collaboration, you either join a collaboration or you leave a collaboration. So here we have WebSocket join collaboration workspace. I made a mistake. I didn't add leave collaboration WebSocket call, but let's say it exists, right? So here we are using WebSocket specifically. When you join a collaboration, a WebSocket connectivity is established from the client and the server. So all the changes done between multiple people will be shared through this WebSocket. So the next one is the collaborators. So this is to get the live collaborators who are making changes for a particular project. I made sure the terminal APIs are pretty basic. So here we have workspaces, ID and terminal. This is used as a API, but you can also use WebSockets for terminal as well. So now that you have APIs laid out, so let's start with the system architecture. And for any system architecture, the client is the basic part. So we will start with the client. They can either be in a browser or they can either be in a different, let's say, iPad, right? So most probably they will be in the browser. Then the next one is the API gateway. If we need API gateway to actually do the rate limiting or do the authorization part of JWT token and get the role based access controls for that. So first service we have is the auth service. So when they are doing the authentication, let's say login or register, that will go to the auth service, and auth service talk with the SQL databases to get the users roles for a particular workspace or for a particular project, and that flow will be done through this auth service. So the next one is the workspace service. So workspace service is a pretty big service here. You can actually divide workspace service and file service separately, but I chose to put workspace service as a single huge service which can be scaled horizontally. So you can talk with your interviewer. If they are not comfortable with it, feel free to change to use separate file service than the workspace service. CRUD operations like adding members, removing members, or getting the roles, and all those done in the workspace service. And then there is also file level operations like getting the file data or saving the changes of a file. All these are routed to this workspace service. Here you can see workspace service connects to the Postgres database for getting metadata, and it also connects to the S3 blob store to actually get the data itself, because remember Postgres database doesn't have the file contents, it only has the file URL which we will store in the blob store. Iteratively I have added cache as well, but you can skip this in the first part of the system design and add it as and when the interviewer prompts for it. So what is the task of this cache is that as the files are stored in S3, the latency to actually get a file is more. If there is a famous project and multiple people are collaborating on a single project, we want to store it in a file so that that can be shared to the users effectively. So I have added a read through cache here. So what it does is that workspace service tries to get the file from blob cache. If it finds, it will be returned. If it doesn't, it will be gone to S3 and that is stored in the cache and then returned to the user. Then we have collaboration path. So this is the largest part where you spend most of your time in the system design interview for this problem. You should be able to talk about how each user get their latest data and how fast do they get the data and how are the collaboration conflicts occur, how do you actually resolve them. All these are actually answered in this part of the system design. So here we have two clients, client A and client B, like Alice and Bob, and as we have discussed, we have an API gateway. So that will use sticky WebSocket routes per session. Why it is sticky is that if a user creates a connection to the server for a collaboration task, we don't want to create a server every time they are sending a request. So that will be a sticky session, and this session is active for a long time and it is refreshed every now and then. So here we have collaboration pod 2 and collaboration pod 1. I've bifurcated into pods, but this is essentially the same service. Pod is just a replica of the same service. So the collaboration service, it has two replicas, and let's just assume that two users are connected to two different pods, two different replicas, right? So a particular client A is making some changes, and that changes have gone to the collaboration pod 1, which has the persistent WebSocket connection. And what it does, it will send the operation to the Kafka operation log. Why do we need this Kafka operation log? Because as we have discussed, every change done on a file, which will be stored in the S3 for backup purpose. So that will be appended to the Kafka operation log, and there is an operation log persister which consumes the Kafka message and stores it in the S3. Here we have Redis pub sub. So you would argue that Kafka pub sub and Redis pub sub is very similar, but it is not. Redis is an in-memory cache, or it is also an in-memory pub sub provider. So why do we specifically use Redis is that when a user does some changes and that goes to the collaboration pod 1 where they have persistent WebSocket connection, that change will be published to the pub sub, and all the users who are in the same collaboration project or workspace, they will consume all the changes done in the project. So here they are specifically not consuming it. Here it is a fan out kind of strategy. Fan out strategy is that if you consume a message from a Kafka, it is you as a client consuming the message. Here if you use fan out, you don't do anything, you just establish a connection to it, and the Redis pub sub provider will just pushes the changes to the collaboration pod where the other users are actually having active connection. If there are like 6 more clients, they will all have a different WebSocket connection and a different pod. As there is a single pub sub topic, you can say topic for each workspace. So when they join a workspace, it will also create a connection in the Redis pub sub for that particular topic. If a change is pushed on to the Redis pub sub for that topic, and all the changes are pushed to the other users in the same collaboration. So this is the major part where you are doing the collaboration service using Redis pub sub to actually send the changes to other users. So the next one is the search service. So here it is pretty straightforward. You will have a search service which will either search the file name or the content, and we will be using Elasticsearch, which will use an inverted index which is faster than the traditional search for other like Postgres or MongoDB databases. And this should be having fresh changes for each file or for each project. How would that have a fresh changes? Here you would see workspace service can send the file events to a Kafka operation log, which we have discussed in previous slide. And there can be another service like called indexers, which will also consume the same message, and that will push these changes to the Elasticsearch. So if there is another person who is searching for the content, that search can be done in this Elasticsearch, which will have the latest data. The last part is the terminal service. So terminal service is a tricky part to implement because there are so many malicious users, and we don't want to create a SSH session to our servers. So the way I want to implement is that we will spawn a virtual terminal for each user in a particular terminal pod, which can be used by let's say Kubernetes, and that terminal service will connect to the S3 blob store and Elasticsearch. Because what do they do in the terminal service? They'll try to get the data, they'll try to do the cat, or they delete the data, like typical stuff which can be done through the UI as well, right? So all those workspace file changes can also be transferred this through terminal service. So we have a blob cache like we have for workspace service between the S3, which will be connected by terminal service. And for workspace it can be mounted here, like we can store all the workspace data in a single bucket, and this terminal service can mount to that bucket so that they can have like they can do the ls commands efficiently. And when they are searching for, let's say, grep, it can be done through the Elasticsearch. So that's why we have a connectivity between terminal service and the Elasticsearch. So previously I have discussed we could use APIs, REST APIs for the terminal, or also we can use the WebSockets. So here I'm using WebSockets for the terminal service. And this is the entire project we have, which has all the paths. Here again I specifically separated collab pod 1, collab pod 2. This can be the same service. I wanted to show you the fan out pattern, that's why I have it as separate pods here. That's all for VS Code in a browser. So I'll be showing you the actual Excalidraw diagram I've done, as I've done in the previous YouTube system design as well, because I have used AI in this content but not in the perspective of the design. I've designed based on what I think I would say in a system design interview, and based on that I've used UI to create all these illustrations. Here we have functional requirements, non-functional, back of the envelope, and we have entities like this is how I would draw, and all the APIs and what data does it take, what does it return and stuff. And this is the actual system design. So here we have API gateway and load balancer before the horizontal scaling for each service, and you don't need to draw the load balancer for each service, let them know that the load balancer exists. And there is PostgreSQL DB, and this workspace service will push onto the message to Kafka, and which will be used to update the Elasticsearch and also persist changes. When it is persisting the changes, it should also update the blob URL, because workspace service will also be adding the metadata. And collaboration service, workspace service will push the message to the Redis pub sub, and that edits of the file will be sent to the collaboration service. And this collaboration service is having an active WebSocket connection between the clients and the collaboration service here. So this is how I would design the VS Code in a browser. If you have liked it, please do subscribe and like the video.